So yesterday we talked about a couple new derivatives. We're going to go back through some of those today and apply them to some of the concepts that we talked about last unit and this unit, and go from there. So the next spot in your notes where we left off kind of yesterday says this: find the equations of the tangent line and the normal line to the curve f of x equals 3 cosine 3x at the point where x equals pi over 9. And so if you remember this, we were finding the tangent line, and when we found the tangent line, we used point slope form. And so if I look and see what I have here in this problem, the thing that they gave me is they gave me x is equal to pi over 9. So I could plug that in right now, x minus pi over 9. Now, a couple things I got to go find. Two things specifically I got to go find. I got to find the slope and I have to find the y value. All right, I'm going to find both of those by plugging in the pi over 9. It's just a matter of where I plugged it in. If I'm looking for slope, then I'm going to take and I'm going to go find my derivative. So if I do the derivative of what I have, yesterday we talked about the derivative of cosine. The derivative of cosine is negative sine. All right. So this is a chain rule, negative sine of 3x. We have an inside piece to 3x that I'm going to now take the derivative of and multiply it on. So my derivative would be negative 3 sine of 3x. Now, when you saw the pi over 3, you might have thought, oh, that's great. That's pi over 9 is not a very easy one. That's not one of our typical ones. But look what happens when I plug it in. When I plug that in, 3 and pi over 9, what that gives me is pi over 3. And pi over 3 was one of those ones that we could do. So pi over 3, if I count my fingers, pi over 3 is a 60. Sine would be square root of 3 over 2. And then I'm multiplying by the negative 3 out front. So the sine of pi over 2, sine of pi over 3 is 3 pi over 2 times negative 3. So my slope in this case is negative 3 square root of 3 over 2. Not super pretty, but I can find that. I can go from there. The other thing I want to do is I want to take this pi over 9 and I want to plug it into the original. So if I plug it into the original, that gives me y values. So cosine of pi over 9 times 3. Again, it gets me cosine of pi over 3. All right, that is an angle I know. So I'll put 60 on my finger again. I'm looking for cosine. I get square root of 1 over 2, or I get 1/2. So y minus 1/2. So I've got that set up. That is the equation for my tangent line. All right, and then it asks what is the equation for the normal line. You got to remember the connection there. The point is the same, so I don't have to do anything with the point, but my slope is perpendicular. So if I were to flip it, change it to the positive, then there would be the answer. Probably don't want to leave it that way. I'd go in and multiply by square root of 3 over square root of 3. And so if I did that, I'd get 2 square roots of 3 over, I'd have 3 times 3, which would be 2 square roots of 3 over 9. So that would probably be a better slope than that. That's the same idea, but it's there. Okay? So we're applying a concept that we talked about previously, but now we know a little bit more about derivatives of sines and cosines, so we can go to that. Okay? I got a little bit of a mixture on the next couple of questions here. We're just going to go find the derivatives. All right? Now we got a mixture of sine and e to the x and some of those things. So we did a problem like this yesterday, that if I was going to take the derivative of that, if I see e to the x, I'm going to write e to the x down. So e to the 2x. I do have that 4 out front, but now don't forget to take that derivative, so I'm going to multiply by 2 is the derivative of the inside piece. So overall, this piece right here is 8, 4 times 2, e to the 2x. So that's the first part of that derivative. The second part of the derivative is here. The derivative of sine is cosine. And again, as another chain rule, so I'm going to leave the 3x plus 2 alone. Then I'm going to take the derivative of the inside piece, which is going to be 3. So the derivative of 3x plus 2 is 3. typically we put that out front, so 3 cosine of 3x plus 2. And there is my derivative. Okay. If they were asking me to find tangent line in this one or whatever, I got a little bit more to be able to plug in. If they were asking me to do it by hand, they might ask me to do that with if x is equal to 0. So if I put x minus 0 over here, then I could pretty easily plug in the here. I got 2 to the 0, so e to the 0 would be 1, so that would be 8. I plug a 0 in over there, all right, and I'd get 2, which I really can't take the cosine of 2, can I? That would be undefined, that does not exist, all right? So I'd probably have to pick a different value there when I would evaluate that, okay? All right, let's continue on. So if we go to this one here, I've got e to the x times sine of x. This is a product rule problem. I'm multiplying there. So if I were to do the derivative, the product rule states take the derivative of the first, which is e to the x, times the second, plus the first, times the derivative of the second. So the derivative of sine would be cosine. And so there would be my derivative. Now, I've got a mixture of function here that sometimes makes it hard or difficult to use. And so what I can look at on this one is I do have a common factor of e to the x. So I could factor that out and say e to the x, and then I'd have sine of x plus cosine of x. The thing that might be helpful about that is I've kind of split my functions. I got like trig functions in the equation, in the parentheses, and I got like that exponential function on the outside. So I can kind of separate them and work them differently if I need to, especially if I was going to try to find, I mean, if it asked on this one right here, if it asked me to find maxes and mins, all right? So I'm trying to find where this is equal to 0. If I was going to do max and mins, where is this equal to 0? Well, if you think about what e to the x is, e to the x is exponential function. Where does that equal to 0? Well, it doesn't. It's got a horizontal asymptote there, so I would get no solutions from that. And then I'd set 0 equals sine of x plus cosine of x, and I can go solve that. I move either sine or cosine to the other side. So I'd have sine and cosine equal to each other. So they're equal to each other at 45, or at power 4, but one's positive, one's negative. So I would have to operate in the second quadrant or the fourth quadrant. So I want the power 4 there. So we're looking at 3 power 4, 7 power 4, excuse me, if I was looking for maxes and mins. That's where they'd potentially be. All right, we're going to look at a problem like that here in a minute. All right, do a couple more derivatives here. This is product rule again. But when I take the derivative of the first, if you remember from yesterday, that 3 is the outside piece. So I would go 3 cosine squared of x. I got to knock that down a degree. Then I would take the derivative of the x, which the derivative of x is 1, so that's not really going to do anything, times the sine of x. So derivative of the first times the second, plus the first, which would be cosine cubed x, times the derivative of the second. Derivative of sine is cosine. So if I were to put all this together, kind of simplify this as I'm going, I have 3 cosine squared x sine x, and I have cosine to the 4th x, because I have 4 of those there. So I have that. Now again, you could take greatest common factor if you'd like. You could take out a cosine squared x, and that would leave me with 3 sine of x plus cosine squared x. Might be helpful if I'm trying to solve, but just understand that we can do that. Okay? Going to the next, we have a natural log. So we talked about natural logs yesterday. Whenever I'm doing natural log, that's the outside piece. So if I were to take the derivative of the outside piece, I'd do 1 over whatever inside of parentheses. So that's what the natural log derivative looks like. It is a chain rule, so I've got to take the derivative of the inside piece now, which is cosine of t. And if I were to put that together, I have cosine t over sine of t. You can leave it like that if you'd like, or if you remember, that's not quite tangent. Tangent sine over cosine, so this would be cotangent of t if you'd like to write it that way. Okay. All right. Moving along. Actually just noticed that I did one thing incorrectly on over here. You may have caught me already. But when I was taking the cosine of x here as my inside, I got sine of x. Technically, it's a negative sine of x. So there should be a negative involved here. That should have been negative. That negative could have gone out front with that 3. Sorry, I missed that piece as I was going. Just wanted to clarify that before we continue. All right. On the next one, we're going to do a little bit of graphing because we've been doing some graphing lately. All right. We're going to do some graphing using our first derivative, our second derivative, like we've done recently. All right. So on this, it says consider the function f of x equals sine of x plus cosine of x for, there's my domain. If you remember, 0 to 2 pi, that means I'm going around the circle one time. It says find the x and the y intercepts. So if I'm thinking about x and y intercepts, I think probably the easiest ones to find would be the y intercepts. So if I were to plug a 0 in here and I were to plug a 0 in there, 0, the cosine of 0 is, the sine of 0 is 0. The cosine of 0 is 1, and 0 plus 1 would be 1. So 0, 1 would be one of my, it would be my y-intercept. Okay. If I was looking for x-intercepts, I would plug 0 in for the y, or for the f of x, and I'm going to go solve sine of x plus cosine of x is equal to 0. We actually just mentioned this one just on a previous problem. I would move one of these to the other side, so I would make negative sine of x equals cosine of x. What angle measure is sine and cosine the same? That is power 4. But again, it's not power 4 because one's negative and one's positive. So we're talking about this quadrant there or this quadrant there. So my x-intercepts would happen at 3 pi over 4, 0, and at 7 pi over 4 and 0. Now, at the bottom, I'm skipping ahead just a little bit. It says use the information that we found from A to C to sketch the graph. Well, these 3 points are going to be very critical points on my graph. I'm going to make sure I put those on my graph in a minute. Okay? All right, moving on to question B. It says find the intervals on which f is increasing, decreasing, and the relative extreme points. So it's asking me to find max and mins. Where do I find max and mins? I find max and mins on my first derivative. Okay? So if I were to take the derivative of this, derivative of sine is cosine. Derivative of cosine is negative sine. I want to take this and I want to set this equal to 0. Okay? So if I do that, it looks very similar to a problem I did just a second ago, except this time cosine of x is going to equal to a positive sine of x. So this is when they're exactly the same. So when are they both positive, or when are they both negative? So they're both positive on 1, they're negative in 3. So we're still talking about pi over 4, but in this case, on my number line, I'm going to put pi over 4, and I'm going to put 5 pi over 4. That's when those two things are the same. So I'm going to go test. That's when that equals to 0, all right? So these are my potential max and mins. I'm going to test some points. I'm going to test 0. I'm going to test pi. That's an easy one that's in between those. And I'm going to test 2 pi. Now the nice thing about testing 0 and 2 pi, it is the same point. So whatever I get for one, I should get the other. So if I plug 0 in, Cosine of 0 is 1. Sine of 0 is 0. So 1 minus 0 would give me 1 or positive. So I'm positive there and I'm positive there. Okay? If I were to go test pi, cosine of pi is negative 1. Sine of pi is 0. So I get a negative 1, which is negative there. Right? So what have I just found there? I'm going to kind of take my B and I'm going to move it down here. I know that my graph is increasing when my slope is positive. So from 0 to pi over 4, it's increasing. And from 5 pi over 4 to 2 pi, it's increasing. Now, why am I saying 2 pi? Why am I saying 0? Because that is what my domain is listed up here as. Okay? It is decreasing the other spots on the graph from pi over 4 to 5 pi over 4. It's decreasing. Now, if I'm taking a look here, this is slope, so I'm going positive slope to negative slope, so this one is a maximum. Negative slope to a positive slope, so this one's a minimum. But what I'd like to do though is I'd like to go find that actual point. So if I'm looking for points, I'm going to take the pi over 4, I'm going to take the 5 pi over 4, and I'm going to go all the way back to the original problem. So I'm going to plug in a pi over 4 here, and a pi over 4 there. So sine of pi over 4, put my 45 finger down, the sine is square root of 2 over 2, and the cosine is square root of 2 over 2. If I were to add those two things together, they do have common denominators. If I add them together, I would get 2 square roots of 2 over 2. These 2's would cancel, so I'm talking square root of 2. So pi over 4 square root of 2 is my max. If I did the same work here, but I plugged 5 pi over 4 in, 5 pi over 4 is the location that cosine and sine are both negative, so it would look the exact same, except they were both be negatives. I would add them together and I get negative 2 square root of 2 over 2. And so my minimum is happening at 5 pi over 4, which is happening at negative 2 square root of 2 as the y value. So I've got my increasing and decreasing, I got my max and my mins, I have some roots, and so I'm going to go do the last thing here. I'm going to go find the concavity and the inflection points, all right? So if I'm going to find that, I'm going to go do the second derivative. So if I look here, derivative of cosine is negative sine. Derivative of negative sine is negative cosine. That is my second derivative. I'm going to set it equal to 0. And if you notice, this looks familiar to another problem. If I move the sine of x over, it would become positive. The cosine is still negative. I'm finding where they're equal to each other, but they're opposite signs. Those are the exact same things that we did up here. So on this sine chart, I'm going to use the 3 pi over 4 and the 7 pi over 4. Those are my potential inflection points. Okay? If I were to go through here and test, again, I'd probably test 0. I'd test 2 pi, and I'd test pi. If I plug 0 into this equation right here, sine of 0 is 0, cosine of 0 is 1, but there's a negative out front, so that's negative. Since 2 pi is the same one, that would be negative as well. If I plug pi in, sine of pi is 0, cosine of pi is negative 1, but I got a negative out front, which turns it into positive. So if you notice, I go from negative to positive and positive to negative, so 3 pi over 4 and 7 pi over 4 are inflection points. Typically, I'd go back and find the y values of that. I'm not going to do that right now because I have already done that up here. So these x-intercepts are also the inflection points. So those are my inflection points. And if I'm listing here concave up from 3 power 4 to 7 power 4, and I'm going to be concave down the other two locations. So concave down from 0 to 3 power 2, or 3 power 4, excuse me, and from 7 power 4 to 2 power. Okay. Got quite a bit of information here. Last thing is it says, okay, go graph this. So if I were to go take a look at a graph, the first thing that I'm going to do is I'm going to put my y-intercept on 0, 1. That's coming from the very first, from A. And I'm going to put my x-intercepts on, which are 3 power 2, 3 power 4, and 7 power 4. So that's pi, this is power 2, this is 3 power 2, and that's 2 pi. That's my quadrantals. So 3 power 4 would be located right here, and 7 power 4 would be located right there. So those are my x-intercepts. I got my y-intercept, I got my x-intercept. Okay? If I go plot my maximums at power 4, this is power 4, I'm going to be at square root of 2. Square root of 2 is 1.414. That's there. At 5 power 4, I'd be there, and I'm going to be at my minimum, which is going to be a negative 1.414. If I'm looking at my increasing, I'm going to increase to the purple. I'm going to decrease till I get to this purple, and then I'm going to increase the rest of the way. So I'm going up, down, back up. All right? Concavity. By the way, these two are my inflection points. We verified that a while ago as well. It is concave up in between these, so it's going to be facing upward, concave up. And it is concave down, facing there, and concave down, facing there. So there is a picture of that graph. All right. Let's do one last thing. Let's take a look at this one real quick. Show how to use the second derivative test to find the x-coordinate, x-coordinated of the relative extrema from there. All right. And then it asked me to find the global extrema of a different equation. So these are really two different problems. So if I'm looking to go find my max and my mins, I'm going to take the derivative of this. So if I take the derivative of that, derivative of natural log of x is 1 over what's inside the parentheses. I would take the derivative of x, but it's 1, so it's not going to really do anything. So that's that first part. Derivative of sine is cosine. Okay. I would take, and I would, if I'm using the second derivative test, I'd go find the second derivative. So if I was going to find the second derivative of this, I would move the x up, make it -1, put the -1 out front, take 1 away, and it would be x to the -2, which I would fix. Cosine would be a negative sine of x. So there's my two derivatives. Now, this is pretty much a calculator problem, all right? And so what I'm going to do is I need to go find where this is equal to 0. Where is the first derivative equal to 0? All right? That's going to tell me what my max and mins are. So I'm going to set that equal to 0. That doesn't look like it's a really easy problem. So this is definitely a calculator. I'm going to go take a look at my calculator. So if I were to do that, come over here. I'm just going to start fresh. So new. No, I'm not going to save that. And I'm going to add a graph. I'm going to do 1 divided by x and then I'm going to say plus cosine of x. And when I graph that, I actually got a pretty decent graph there. It's in degrees right now, but really I probably should change it to radians. That is a better picture of that graph. We see a lot more of that graph there. All right. Now, I'm looking on this graph, I'm looking for my zeros, and I'm looking from 0 to 2 pi. So if you notice here, 2 pi would be 6.28. So I can't have anything bigger than that. So if I were to go find my, go analyze graph and go find my zeros, I'm going to start here. The first zero I come across is 2.07. The next zero I come across is 4.49. If I were to keep going, I kind of run out of room there. I'm going to escape out of that. I'm going to do that again. I'm going to go menu and analyze graph. And I'm going to go zeros again, but I'm going to start closer over here. And when I do that, when I get 7.98, well, the 7.98 is bigger than 6.28, so that's outside of my domain. So the two numbers that I got were 2.07 and 4.49. So if I were to put those on the number line, 2.07 and 4.49. Now I could test that, or technically I could look at the picture because we've been doing a lot of looking at pictures. It's above the x-axis, so it's positive to start, then it's below, so it's negative, and then it's positive again. All right, or I could plug in numbers, so positive, negative, positive, all right? And so this would be a maximum and this would be a minimum. Now, granted, that's not what it asked me to do here. It asked me to find the second derivative, use the second derivative to prove this. And so what I really need to do is I need to take these values that I got and I would go plug them in. Okay? So if I plug that in, then I'm just going to help you with this. I used my calculator to do that. It's not something that's super easy. And so if I plug that in, I got negative 1.11. Well, because this is a negative number, the second derivative kind of works opposite of my normal thinking. If I plug in the second derivative and it's negative, then that means that that was a maximum. Okay? So I kind of verified that as well. If I took this 4.49 and if I plugged it in, I got a 0.975, which is a positive value. So that's going to be working opposite. I'm going to think minimum when I see that. Okay. Again, I like my number line over there. I only did that last little bit is because it said to use the second derivative test to find that. Okay. All right. Don't really have time to do that last one. We'll end there for today. I know it took a little bit of, maybe a little bit longer than normal. So we're working on page, let me look at it real quick. 551 and 558 is where that is set up for you. Let me take a quick look at that. So 551, we're just doing some more derivatives there, 1 through 13, and then doing a couple applications. I think the odds would be really good for that. That's about 7 problems there. And then on page 558, we're doing one question. We're doing question number 3. Okay? And I would probably work that. 3 is a pretty good challenge. And we'll look at it. We'll probably discuss that when I get back.